Today's lecture is about motion planning. Motion planning is essentially the problem of computing a path that gets a robot from point A to point B. We're not going to worry about velocities, accelerations, dynamic effects. It's strictly about the path that the robot takes to get from a start to a destination. So motion planning is also often referred to as path planning. So in this context, you've already seen one form of path planning. And if you think about it in that sense, the Cartesian control approach that we looked at in the last lecture is, in a way, a form of path planning, right? If you think about a robot arm, the end effector is at a given point in space. We'd like the end effector to get to a different point in space. When you do Cartesian control, you are computing a path that the robot takes to get the end effector to the desired destination. And that path has a specific characteristic that we discussed last time, in that the robot does its best so that the end effector takes a straight line from the start to the goal. That's what Cartesian control does. You compute the joint movement such that the end effector takes, in as much as possible, a straight line path from the start to the goal. And that's fine, it works in many cases. What if the straight line path for the end effector is blocked by an obstacle? How do you get from point A to point B? In that sense, the end effector cannot afford to always go directly towards the goal along the shortest path. It needs to go around obstacles. The robot needs to plan a path. And that is one of the core topics of today's lecture. There is a little bit of a different flavor to the way we approach motion planning, in that we assume that we already have a pre-computed robot configuration that places the end effector at the desired location, right? So this is where the robot is now. This is where we'd like the end effector to be, and we've already computed the inverse kinematics, which have told us, hey, this is a robot configuration that gets the end effector where we need it to go. Now, the problem is, how does the robot move such that it goes from the current configuration to the goal configuration without hitting any of the obstacles? How does it plan a path in its environment that gets it from one configuration to another without hitting anything? And interestingly, this problem isn't applicable only to robot arms. It's extremely applicable also to mobile robots, and in a very similar form. So here's a mobile robot. Let's say it's a wheeled robot. And in the next lecture, we'll be talking a bit more about how do you model the ability to drive of a mobile robot, the ability to execute trajectories. But let's think that for a second, this is a wheeled robot that can just drive around its environment. This is where it's starting. This is where it needs to go. There are obstacles along the way. It needs to plan a path that gets to the goal and doesn't hit any of the obstacles. And the interesting thing is, these two problems are remarkably similar, even though at first glance they seem to be quite different, right? This is a case where the entire robot moves. It's a wheeled robot. The whole robot just gets up and goes. Whereas here, the robot as a whole, right, the base is still fixed. It's just the joints that change values. It's an articulated robot that doesn't move as a whole. It just changes its joint values. So how are these two problems really, really similar? And in order to see that they are extremely similar, we have to reason not about the robot arm in Cartesian space or in task space, but rather about the robot arm in joint space, also called configuration space. So let's remember what that means, right? So let's say we have a simple planar robot. So we have our coordinate frame. And then a very simple planar robot, which has two links, right? So this is Cartesian space. We have x and y. And then this angle here is q1. This angle here is q2, right? And this is where the end effector ends up. So in Cartesian space, we have a point, for example, bold x will have the position of the end effector expressed in Cartesian space. In joint space, right, a point in joint space, a vector will be a vector that will give you the values of all the joints. Okay, so in our case here, let's say that Cartesian space is two-dimensional if we only care about the position of the end effector and not its orientation. Joint space, also called configuration space, is also two-dimensional because the robot only has two joints. Okay, and now let's say that we have an obstacle. I'm going to plot the obstacle, for example, right here in Cartesian space. What does this obstacle mean for us in joint space, in configuration space? So let's plot in configuration space the robot configurations that are illegal because they intersect that obstacle, right? So if this is Q1 and this is Q2, right now I am doing plots in configuration space. So this is the value of the first joint. This is the value of the second joint. So let's look. What cases do we have robot configurations that put us in collision with that obstacle? And for now, we're going to assume that this obstacle is infinitesimally small. Okay? So first of all, obviously, if the robot points towards the obstacle and it's perfectly straight, right? This configuration is illegal because the second link intersects the obstacle. So here, Q1 has some values. Let's say that this is maybe 30 degrees. So Q1 has a value of 30 degrees. Q2 is 0. So this point right here is illegal in configuration space because it intersects the obstacle. But that's not the only configuration where the robot intersects the obstacle. For example, the robot could also look like this. And this is also an illegal configuration because the second link hits the obstacle, right? So in this case, Q1 is, let's say, 45 degrees. So maybe Q1 is right here. Q2 here is negative, let's say, negative 60, right? So Q2 is right here. This is also illegal because the robot intersects the obstacle. Similarly, for example, if I plot my robot like this, where the end effector just hits the obstacle, right? Now I have a negative value for Q1, so this is my Q1, and I have, let's say, 90 degrees for Q2, and that's illegal because it intersects the obstacle, right? So for a negative Q1, and then let's say 90 degrees for Q2, this is also illegal because it intersects the obstacle. And now you're getting the sense that, look, there are many, many configurations that will make the second link hit the obstacle. And in fact, all of those will give me an illegal point somewhere in joint space. So there's some curve here that connects this. That's, for some cases, it's not necessarily a straight line, but it's certainly some curve that is comprised of illegal configurations in joint space. So this point obstacle in Cartesian space gives me this entire range of illegal configurations in joint space. If, let's say, the obstacle has a little bit of heft to it, it's not just an infinitesimally small point, but rather it's a line. Sorry, but rather is a circle in Cartesian space. So let's draw that case, right? So now our obstacle maybe looks like this. What happens to the image of the obstacle in configuration space? Well, again, when Q1 is 30 degrees, so now we are right here, so we are along this line in configuration space. Now you can see that there are a range of values for Q2 for which the robot hits the obstacle. Here it hits the obstacle, here it hits the obstacle, and for everything in between, it also hits the obstacle. So now, for this entire range of Q2 at Q1 equals 30 degrees, all of this is illegal. And then if you carry out this exercise for multiple possible values of q1 and q2, you see that this line that we drew before actually gets a little bit of thickness to it. So the model of the obstacle in configuration space looks maybe something like this. Okay, so any combination of q1 and q2 that falls inside of this area is illegal because it causes the second link to hit the obstacle. So what we've done is we've mapped this obstacle from Cartesian space into configuration space.